So the game, you have to find the invisible cow, okay? By sound. So it's like by sound. So it gets hotter.
I'm Jacob. I'm in second year computing with a focus on AI and a minor in math.
I'm Jesse. I'm in second year computer engineering.
I'm Anne. I'm in second year applied math engineering. We're also missing two of our team members with us today. Jack, who's in third year computer engineering, and Danny, who's in second year computer science.
And we're on the DAIR Imaging Robotic Traversal team. We're looking to use computer vision and inertial measurement unit sensor data to assess path traversability. So the purpose is to assess how traversable a path is. And in first semester, we dove into looking at the inertial measurement unit sensor data, and we tried to classify what surface you were driving on based on what the robot feels.
We used PCA to visualize the high-dimensional data, and we used a variety of different techniques to try and classify the terrain based on the sensor data.
Of the various different techniques we used, we included k-nearest neighbor and k-means as a way of grouping points that were unknown with points that were known. We also used different various techniques such as logistic regression, neural networks, and recurrent neural networks.
So we started by using label image to draw bounding boxes on all of the images of potholes to get the upper left coordinate as an XY coordinate and then the width and height of the bounding box. We used Pascal VOC to save those annotations, pandas to iterate the directory for labels, and then do the same for images.
So one technique that's really important in any sort of deep learning is data augmentation, because a network can learn to overfit its training data rather easily if it's complex. And so data augmentation is one way to introduce more variety into your data set. So what we did is we wanted to take each image and then randomly rotate it a certain number of degrees within a window. And we also wanted to flip it left to right randomly. And so that way, as your model trains for more epochs, it's not seeing the same images over and over again. It's seeing slight variations of those images. So what we did, you can see our work here, which you can succinctly define this work here as we were trying to rotate a bounding box. But it turns out to rotate a bounding box, a set of 4 Cartesian points, is quite difficult in the Cartesian coordinate system. So we moved those points so they were relative to the center of the image, which is where the image is being rotated on, and then we converted the coordinates to polar coordinates. And polar coordinates are when you represent a point as a distance from the origin and an angle from the x-axis. And so once it's in that form, then we can rotate the labels to match the images. And so we defined a custom batch generator. And so what it will do is it returns the length of each epoch. It has a function that runs after every epoch and a getItem function that returns a batch of labels and images. And you can see that it will randomly rotate an angle in a range, and it'll randomly flip the images. And so you can see, here's a sample image set. So the images are rotated and the bounding boxes have been moved to match the potholes. So you can see, even though the images are rotated, that the bounding boxes still match.
So for our model, we use a convolutional neural network composed of 4 convolutional layers, along with a dense layer and linear activation. We use Atom as the optimizer for our model, and we've comprised it of 100 epochs running through the model. And as you can see from our loss graph, we're not experiencing overfitting, which is very promising for the success of our model. And as you can see, we're having a degree of success identifying the bounding boxes of potholes. The green represents where we have personally annotated the pothole to be, and the red is where the model thinks the pothole is. Many of these images are very similar, so we are seeing a higher degree of success. By introducing more varied data, we'll be able to more accurately judge whether our model is succeeding and perform better analysis of unknown potholes.
In second semester, we pivoted a little bit, and so we wanted to utilize the camera on our robot to identify, localize, and then avoid potholes. So we're working on the robot operating system, which allows us to create a set of ROS packages or nodes. And these nodes work asynchronously, they can all run in parallel, and they can communicate between each other, along with a number of built-in nodes that come with ROS. And so we've implemented a couple of these such packages, such as a package for pothole localization, which relies upon a model that we trained in Keras on TensorFlow to do a regression on 4 points to output a bounding box in an image around where a pothole is. We used a convolutional neural network, and the output, like I said, was a regression on 4 variables. The x-coordinate of the top left point, the y-coordinate, the width, and the height of the box. This is published as a ROS topic and received by the control node.
So the control node will take in the bounding box that we've generated around the pothole and then attempt to steer the robot around that bounding box and then return it to its initial path. We've experimented with different avoidance algorithm models to do this and have settled upon a potential field method which treats the goal of the robot as an attractive force and the pothole as a repulsive force, allowing it to kind of steer around said obstacle and return to its desired path.
In order to do this, we needed to calibrate the camera from the coordinates of the bounding box in the image to the coordinates in the real world, so in the 2D plane just along the ground. To do this, we had to calculate a matrix that would allow us to calculate all of the real world coordinates of the bounding box.
And a final ROS node that we're implementing is a node for classification. This will tell us if there is actually a pothole in the frame, and that way our controller node knows whether to actually listen to the output from our localization node. There is definitely a learning curve. Me personally, I've done a fair bit of machine learning and image processing, but I haven't done a lot with different hardware. So working with the robot took a lot of learning for me personally to figure out how to use the robot operating system.
Yeah, I was definitely in the same boat for the robotic operating system in that it was very new to me, though I also didn't really have much experience with any forms of computer vision or really much machine learning in general, so it has been a very steep learning curve, but it's going very well, I think.
My experience was similar with being unfamiliar with the ROS operating system, but I also had very limited experience with coding in general, so there was a very steep learning curve, and I'm definitely still learning with this project.
So I think the biggest challenge that we as a team went through was throughout first semester, we were collecting the sensor data and we're using PCA to visualize and all these different classification methods to try to make sure that the data actually matched up very well with what we were driving on. But after applying all of these different methods that Jesse described, with a lot of fine-tuning, our accuracy still wasn't reaching a high enough point that we could confidently identify the surface. We ultimately realized that due to hardware limitations on the sensor, we weren't able to classify what surface that the robot was driving on. So we had to pivot a little bit. So that's why this semester we are working more with the camera and we are trying to look at traversability in terms of is there a pothole that could damage the robot or not.
First semester, we adopted much more of a independent model where we would do work outside of meetings, and then during meetings, we would share our work, discuss our outcomes, and then assign new tasks for the next meeting. We found that this led to some difficulty with members such as myself who didn't know as much going into it and therefore struggled a bit more. For second semester, we adopted more of a collaborative effort. So we would have one meeting a week where we would discuss kind of goals or objectives for the week and assign tasks. And then our next meeting would be a longer one in which we could sit down and work on things together, get help from other members, and kind of combine our efforts more as working on them so that we would create a stronger outcome and just be able to get more done together than we would be able to separately.
So right now we have these different ROS packages in progress, almost completed, but we really need to do some integration testing and see how they all fit together. So one of our challenges is that currently, it's winter in Canada, it's snowing outside. So that makes getting data and training on new data pretty difficult because the potholes are filled in with snow, and our robot is not an all-terrain robot. So we need to kind of figure out a creative way to showcase our robot being able to avoid the potholes at the conference, but also a way that we can experiment with that right now so we can test and make sure that our methods are working.
To build off of that, we also need to further test and potentially iterate the camera calibration matrix.
Finally, we need to implement the avoidance algorithm to make sure that the robot, once a pothole is identified, can avoid it without crashing into it.
That's awesome. Thank you so much for sharing your project with me.
Awesome, thanks.
Thank you.
Thank you.